Hi, and welcome to Fluid Dynamics 1. A few of you asked me to go a bit deeper on fluid dynamics, so that's what we're going to be doing this lesson. Just really drilling into some of the basics, because a lot of this devolves into really complicated maths really quickly, which you're all going to be going to do a lot of that, but I just don't think me, with my bad maths, teaching you through YouTube videos is the best way for you to learn that. So what I'm going to do is sort of cover some more conceptual ground. So we start with water flowing through a pipe. So I want you to imagine this pipe is completely full of water and it's gushing this way. Just water's flowing through. And here, the pipe is nice and wide, and then it's going to thin down and go to a pipe half the length. Okay, so it's going to narrow like that. What I'd like you to just pause the video and think for a moment is, do you think there's going to be any change of speed of water when we go from here to here? Just pause the video, have a little think. The answer is yes, there will be. It will go twice as fast here as it will do here. And what I'm going to spend the rest of this video doing is showing you different ways of thinking about the same properties. So this point of doubling the speed, we can describe that in a bunch of different ways. The simplest and my favourite is the so-called box of water way of doing it. I call it box of water, don't know if anyone else does. So what you want to imagine is we can sort of draw similarly sized blocks of water. So each of these blocks of water has the same amount, some number of litres. Okay? And they are being pushed at a certain rate through the pipe, aren't they? But every time this one moves up, another block of water, same volume, is going to have to come up behind it. We call the mass passing a certain point in a unit time the flow rate. So that's called the flow rate. So if it might have a flow rate of, 8 litres per second, that would just be the flow rate. Think about the flow rate at any point in the pipe has to be the same. You can't have 8 litres pumping through here and only 4 here, because that would mean 4 litres had sort of disappeared. But if we want to chug the same amount of water here and here through in the same amount of time, it's going to have to move a damn sight faster in this part of the pipe than it is in this part of the pipe, therefore it must speed up. We could also just say mass is conserved. We can't just magic mass in or out of the pipe, and that would also tell us that the speed's going to have to double. However, there's a couple of other really neat ways we can look at this. The first is we can talk about momentum, because we know that momentum must also be conserved. And therefore, if we're sort of halving the amount of mass that we've got, we must double the speed in order for linear momentum to be conserved, because we know momentum is just mass times velocity. So we could also explain this process through conservation of momentum. The third thing we can look at, which is really cool, is conservation of energy. And this is where it gets a little bit more enticing. So we know from our study of ideal gases that all fluids have within them an internal energy and a potential energy. Okay? Now, within the concepts of ideal gases, we generally think of potential energy referring to the state and the internal energy referring to the temperature. However, if it's flowing along a pipe, it must have a third type of energy, which will be its kinetic energy. And that's obviously just linked to how quickly it's moving. Now we know that energy must be conserved. When the water speeds up, that energy has to come from somewhere. It can't just gain kinetic energy and not lose energy somewhere else in the system, because energy can never be created or destroyed, which I don't need to tell you. So if the kinetic energy is going up, one of these other two have to go down. And it turns out it's the potential energy which drops, because potential energy in fluid dynamics doesn't just refer to the state of the liquid, it actually refers to something that we call the static pressure of the liquid, which is a representation of how much force there is if you were in that liquid pushing on you at that point, how much the liquid would sort of crush down on you. Lots of things can affect this. If you get a big column of water, there'll be much more static pressure at the bottom than at the top, because if you're at the bottom, all the water above you is pushing down, which is just as you'd expect. This means that you get a really neat thing happening here, which is as the kinetic energy goes up, the potential energy is going to go down, and the pressure, the static pressure, remember how much it's sort of pushing in on itself here, is going to be much less than here. Yeah, kinetic energy, potential energy is going to go down. which refers us back to the Bernoulli Principle that we were talking about the other week, which is that when the speed of a fluid goes up, the pressure goes down, and we get a force between the pressure differentials. So we can also consider that in terms of the energy. There's one final way that we can show it's going faster. If we get rid of these water blocks, and we replace them with streamlines, which, if you remember, were just a sort of showing you where any given bit of water was, what it was doing at that point in the flow. If we start drawing streamlines, and we imagine 5 bits of water, well, this one's going to go bonk, 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 like that. This one's going to go like this. This one's going to go like that. It's going to go like that. And this one's going to go like this. But what we see here is the streamlines have got closer together. And we know from just streamlines that whenever we've got streamlines close together, that represents a higher speed. But we also can just see the streamlines have to get close together because there's less space for them. So therefore, even just using a graphical method will tell you the water will speed up in that part of the pipe. So there you go. Same idea, explained 5 different ways. Hope you enjoyed it. See you tomorrow.